from I/O interfacing. Now, I have told you that your every I/O devices are having address. Okay, so these addresses can be either even or odd address. Okay, and hope you remember during my last class I have told you, right, that if you want to transfer 16 bit of data at a time to microprocessor from I/O devices, you need to have this I/O devices addressed for even and odd address, so that at a time 16 bit data can be transferred from I/O devices to the microprocessor or from microprocessor to the I/O device. Okay, see here. So all these things, the even addresses, these are all even addresses, and all these are odd addresses. And even address, you see that D0 to D7 is connected to D0 to D7, and odd addresses are getting data on D8 to D15. That means totally it gets 16-bit data, right, in one machine cycle from I/O devices. Okay, like you have done the same for memory devices. Okay, this is applied to I/O devices also. Right? The purpose is to get only 16-bit data at a time. Have you understood this? Okay. So I'm continuing from here. Okay. This is just one slide to mention you that I/O devices can also be arranged in the form of even and odd address, so that at a time 16-bit data can be accessed. So hope all of you understood this. Okay. Okay. Next. What is this? How do we separate this I/O devices from the microprocessors? See, microprocessor is an integrated circuit, right? Microprocessor is an integrated circuit. Okay. And I/O devices is something which is connected external to microprocessor. Right? These I/O devices may have high current, okay, may have high voltage compared to microprocessors. So is it feasible to connect, okay, I/O devices directly to the microprocessor? Tell me, can I connect these I/O devices directly to the microprocessor? So suppose your I/O device is drawing more current and having high voltages, okay, compared to what the capacity of the microprocessor. Do you think it can be connected directly? No, right? It has to be connected through buffers. Buffers acts as an isolation between the microprocessor, okay, and the I/O devices. Okay, just remember this is very important. So input devices must be isolated from global data bus. So what is used to isolate is buffers. So what happens? Otherwise, unwanted data, garbage may be transferred on the data bus. Always see that your data bus. See, microprocessor sends or receives data to data bus, right? If at all any data to be transferred or received from the I/O devices, it has to go to the data bus. You all know about it, right? So I have a global data bus in my microprocessor. I cannot connect directly to the I/O devices because I/O devices current voltage may vary, which may spoil your entire microprocessor, 8086 microprocessor. I understood this. That's why we connect something called as buffers. You all know about buffers, right? Right? You all know about buffers. Buffers we have already discussed. 74LS244. Hello. Aganandan.
Yes, sir.
Class is going on, you know, right? Recording is going on here. Right? I was talking about the buffers and why the buffer is required. I have already mentioned to you. Okay? So now we have also used latches and buffers with the memory interfacing. So memory has such as latches and buffers internally, present. See, listen carefully here. Why this is not used with the memory? Why we are going to use buffers with only IO devices? Why we are not using with the memory? The question is, memory already has the buffer inside it. Hence, we are not using separate buffers for the memory. Otherwise, whenever you connect memory also to the microprocessor and also IO devices to the microprocessor, you need isolation. You need isolation because everything is going to be an integrated circuit. Your 8086 also an integrated circuit, and your memory devices are also integrated circuits. All these are ICs. If you are connecting these two, you need to have an isolation. You need to have isolation. Suppose if you are connecting these two IO devices, you also need an isolation between this. Right? So here we use buffers. Here also we use latches and buffers which is available internal to this memory devices. So internally you have this, so that externally connecting a buffer is not required for this. Okay? Okay. How do you interface? How do you interface your IO device? Can I face it directly, or I need something to be connected between that? Okay. So any microprocessor systems, when data is sent out by microprocessor, the data on the data bus must be latched by the receiver output device. As I told you, memory has the internal latches to store the data. Now this latching system must be designed by ports. What is this ports? Hope you have done these experiments in the laboratory, right? When you have connected a microprocessor to an IO, okay, you are going to use one programmable peripheral interface called as A255. Okay, so after that you connect an LED. Okay, after that for this you connect an LED. Okay, so see, between microprocessor and your LED, which is an IO device, this acts as a buffer or latch, right? This acts as a buffer or latch, right? So that's what I'm trying to explain you. Okay, see, the data provided by the microprocessor is available only for the short period of time between 50 to 100 nanosecond, and that data must be latched, otherwise it is lost. Okay, so similarly, when the data comes in from the port memory, that must be, see, can you tell me why we need to use a latch between the IO device, okay, and the microprocessor? Now, can you tell me in terms of a very simple word, what exactly latch is? What exactly latch requirement is?
Retention of data.
For
Retention.
exactly retention of data. Why retention is required?
To send the signal back.
Send
the signal transfers.
No, you give correct answer, my dear. Why I need to see? Microprocessor runs in certain speed, right? Right? But your IO may not be running the same speed, right? It may be little slow in getting the data, but microprocessor will not retain the data, as I told you, 50 to 100 nanoseconds, because it depends on the each machine cycle. But if the IO devices are not in synchronization with the speed by which microprocessor receives or sends the data, you need to keep that data in a latch. I've understood this, right? So what happens is your data will be generated from the microprocessor, and then it will be stored in the latch for temporarily for some small time until your IO devices receives the data. Similarly, when IO devices sends the data to the microprocessor, okay, it will send it through latch. Why? Because it will just keep the data in a latch, so microprocessor will accept it based on its own speed, right? That's the purpose we are having the latch or buffer which is connected between the IO devices and the microprocessor. Okay, so 8255, which is the programmable peripheral interface, is also an example of this. Why every time we use 8255 whenever we want to connect anything to a microprocessor? Because of this reason, right? Any mismatch in handshaking between the IO devices and the microprocessor will be taken care by this buffer or latches. Okay, 8255 is one of the device which is extensively used to interface IO to 8086 microprocessor. That's what we are going to study in detail in forthcoming slides. Okay, so now let us see. You have a microprocessor. I already told you. You have a port or interface controller, and this is your IO. Simple example. This is your 8086 microprocessor. This is your 8255 programmable peripheral interface. And this can be your LED, this can be your 7-segment LED, this can be your motor, okay? This can be anything, okay? Okay. As I told you that you have 8086 microprocessor, you have 8255 programmable peripheral interface, and this LED, or can be an IO device. You have already done this in the lab. There's something hands-on you have already done, right? You have done it using simulation software Proteus. You have done it using hardware, right? So can you tell me, when you did hardware experiment, where is your 8255? Have you just tried to know where is your 8255 when you did hardware experiment? How many of you have seen it? I just wanted to know. How many of you seen where is your 8255? Where is your 8255? Tell me, somebody, don't hesitate. I will not shout you. I'll shout you only when somebody, breaks the rule and, acts so, different way, Okay. Tell me, you can answer me. Don't be shy, or I can be as friendly as with you when it comes to, transfer of knowledge. That's what I find myself, I'm doing something to my profession. Right, tell me, have you observed where is your 8255 is? Can somebody give me the answer in this class? You have done the hands-on. Where is that? Tell me, Nagananda.
Is it in the PC as a software?
It's on the boards.
Did you refer to your manual? How many of you referred to your manual? How many of you referred to your manual? Tell me. Did you see the manual? No. No one has seen it because chalta hai. We are giving full maths to the lab, maths in the lab. So we just submit a journal. Lab. Everybody got full mark in the lab sometimes. Okay. Even though scored 1 or 2 in the theory, in lab everybody got full marks. Right. That's our system. I blame the system, not you. Right? Sorry. It's not your fault. It's our fault. Our system is like that. Okay. Fine. Where is the 8255?
So it's on the board, sir, like close to the microprocessor.
Is it on the board? There is a PCI card. See, that's what I told you. You try to understand this. See, this is I'm just teaching you for your knowledge. I can do my duty by just rolling all the slides, no problem. Right? I believe in knowledge, not completing the syllabus. Right? See here, you have a used PC here, right? PC. You have used a PC, right? Always you have used a PC itself to simulate 886, yes or no? Yes or no? Your experiment number 1 to 7, you have used TASN. You have used TASN to simulate 8086 microprocessor in a i7 processor PC. In a i7 processor PC. See, this Intel has developed every microprocessor in such a way that any instruction you give for its lower version of microprocessor, it will execute. You can execute 8086 instruction in i7 also. Have understood this? So, taking that as an advantage, right? You have simulated some 7 experiments in the PC itself using a software called as TASM. Have you understood this? Otherwise, you will have to do every experiments 1 to 7 in a kit, in a 8086 kit, which is a small kit. Your every experiment would have been horror story if you would have given your kit. I have understood this. We have a kit here, right? We have a kit. Every student would have been given a 8086 kit to enter the program and conduct the experiment and execute all the instructions. The 8086 kit only, which has 8086 microprocessor in it. It is not so easy. Open PC, do copy and paste. Nothing is possible in that. Right? We are not giving you. Right? We made your life easy by just using just PC and use a TASM to do the simulation. Right? Otherwise, if you are using 8086 kit, you will have to use a keyboard, a small display. Your entire lab would have been horrible. Right? We have not done it. We have made your work easy. Right? Now, when you want to do the interfacing using 8255, what to do? This does not have 8255 interfacing on the motherboard of it. So what we did is, this PC has got something called PCI slots. I don't know how many of you know about PCI slots. Your PC has got PCI slots. On that PCI slot, we fixed a PCI board which is having 28255 in it. Go and refer to your manual. Right? So we have used a PCI card in this. In PCI card, okay, you have 28255. It is fixed into the PC. Okay, and then one cable is coming out. One cable is coming out. You must have seen one cable coming out from the behind. That is connected to your IO device. It can be your motor. It can be your, say, whatever kit, 2 kits you have seen, right? What is that? Elevator kit. It can be your traffic light controller kit. Everything is connected through this 8255. So there is 8255 PCI board has been fixed inside the PC. Right? Over that, you are using an operating system for Linux, and on the Linux, you are using Windows 98 to simulate the program using same assembly program what you studied during entire semester here. Have understood this, right? You maybe most of them are asking, sir, why 98? Why Windows 98? Windows XP? Because these whatever board you are connected 8255, okay, it's a little old board. It's not possible for new PC to have a driver for that. I don't know how many of you know about drivers, right? This is where you do the hardware experiments, right? So you have already used 855 in that. You already used 855 in that. Okay? So just for your information, you have the 855 connected to PCS slots of the PC, and through 855 you are actually connecting your IO devices. I understood this. So having this 825 peripheral interface is very important for this. Okay. Now see here, I will ask you one small question. Design 8 LEDs. Design 8 LEDs. Okay. And entire the LED set is having address of 9CH. Okay. Entire LEDs are having address 9CH. See, how can you develop, how can you design this? Don't go by this. Try to do it yourself. Come on. See, it's very simple. Don't go by. If you see this, you will not understand. Okay. See, what you need to connect to your 8086? Tell me. Come on. Try to understand this. This is very easy. It's not difficult. Just give some attention here. Okay. This is your 8086 microprocessor. Okay. 8086 microprocessor. Okay. So you have 8 LEDs here. 1, 2, 3, 4, 5, 6, 7, 8 LEDs here. You have 8 LEDs. Consider these are the 8 LEDs. Normally LEDs are actually symbolized by a diode. Okay. Fine. By a diode with a arrow. Okay. And you can connect all these things to the ground. Okay. Why? Because if you give 0 here, it won't glow. If you give 1 here, it will glow. You all know about it. Okay. Now, I told you that you cannot directly connect the data. See, this is basically taking D0 to D7, right? There are 8 LEDs in this, right? The 8 LEDs here can be made switch on and off based on the data sent to that, right? So there are 8 LEDs. At a time, I can send 8-bit data to this. You agree for this, right? I can send 8-bit data to this. That means I can connect each and every LEDs to D0 to D7. Okay, but I'm not allowed to connect your D0 to D7 directly from microprocessor. I need to have something buffer, right? I need to have something buffer. So what I'm doing, I'm going to connect this D0 to D7 to a buffer. And from buffer, I'm connecting this. Okay, so your D0 to D7 will come here. Fine, I've understood this. Now, what is the address of this? Is the question. 9CH is the address, right? 9CH is the address. Okay, that means you are out of your A19 to A0, your address is 009CH. Yes or no? Your address is 009CH. Okay, that means when the microprocessor generates an address, the enable pin, okay, which is actually G, which is active high for 74LS373 is the buffer. You can see the enable pin has to be high. This has to go high. So when the microprocessor generates this address, okay, 9CH, you should have some combinational circuit here, that it will produce 1 here. I've understood this now. Similar to what you do in memory interfacing. Now, can you get that combination circuit? So this is the input of this combination circuit is A19 to A10, right? Now, when A19 to A10 is 009CH, you should get one here, so that this chip will be selected, okay? And whatever data you put here in D0 to D7, accordingly your LEDs will glow. Have you understood this? Right? Yes or no? Okay, that is what is this circuit. See here. I already told you about this. See, 9CH. 9CH means your A coming from A7 to A0. 9CH means it is 1, 0, 0, 1. Okay, C means how much? Tell me. C. It is 1, 1, 0, 1. So microprocessor, see, remaining address lines all 0, 0, 0, 0. You need not worry about it. Okay. So now here you are giving. This is your A7. This is your A0. Sorry, A6, A5, A4, A3, A2, A1, A0. Right? Is it 1101? 1100, no? Yeah. Now see here, whenever microprocessor receives this signal, this data, see what is produced here. See, you're getting one here, 0, 0, 1, 1, 1, 0, 0. Right? Now you see here, this 0 will become 1 here, it will become 1, everything will become 1, you will get 1, 1, 1, 1, 1. What do you get here? 0. Now, see here, along with the 0, you are connected write signal and IO bar signal. Yes or no? To write the data into this LED, you need IO bar M signal. Yes or no? And also you need write signal. Then only microprocessor will write. No. Now tell me, what is your write signal when a microprocessor want to write the data into the IO? It is 0. Can you tell me what is your IO bar M when a microprocessor wants to write it to the IO? This also 0. See, 0, 0, 0. In a NAND gate, 1 will come here. See, 1 will come here and this will be selected. This will be selected. So now, when a microprocessor executes out 9C H comma AL, suppose if I give in the AL, move AL comma, if I give 0, 3H, if I give 0, 3H, and then I execute an instruction out 9C comma AL, what happens? Tell me. AL is having data 0, 3. 0, 3 means you have 0, 0, 0, 0, 0, 1, 0, 1. Okay, your D7 to D0 is having this data. Okay, and address is 9CH. When out 9CH comma AL is executed, you can see that this particular circuit will, same time your write bar will become 0 and IO bar M also will become 0, because microprocessor wants to use IO and wants to write the data. Accordingly, this will become 0, 0, 0, 1 will come here, this will be selected, and whatever data which is coming here, that is 0, 0, 0, 0, 0, 1, 0, 1 will be transferred to this. Okay, when this data is transferred to this, can you tell me which of the LEDs will glow? This LED will glow, right? And this LED will glow. And all other LEDs will not glow. It is off. Have you understood this? Now, I want to ask you one question in this. Can you write a program, okay, for this setup in such a way that this LEDs will give you, okay, an effect of running light. There are 8 LEDs are there, right? What is running light? Do you know what is the running light? What is running light? One by one it will glow, right? Right. Can you write a program yourself? I have told you now, to make this to LED to glow and all LED off, you have to give 0.3. Can you tell me, if you want to have an effect of running light, can you tell me what is the program you should do in this? Tell me, come on, this is very interesting one. Huh? Anything, tell me, not a problem. So what is running light? First, this will be glowing, right? First, this will be 1, all this will be 0, 0, 0, 0, 0, 0, right? Yes or no? Then, after that, this will be 1, all will be 0, 0, 0, 0, yes or no? Right? Finally, all will be 0, 0, 0, 0, then it will be 1. And then it will repeat, yes or no? It will repeat, that's the running light, right? So you can now write the program. Can you tell me how to write the program for this now? Tell me, yeah. What data I should give first? Move, AL, comma, what data you should give? What is that one? What is the data? What is the data? Suppose if you want to give 10000000, what is the data you should give? 80H, right? So move AL, comma, 80H. Now you do out 9CH, comma, AL. What will happen now? Okay, right? Okay, now what you should do next? Move AL, comma, this will be 0100 0000, right? Yes or no? Okay, then what should come? 40H. Next, immediately you do this. Next time, second LED will glow, other LEDs will be off. Okay, what else next? What is next? Now, next, move AL, comma, 20H. You call out. Why every time I am calling 9CH, comma, AL? Because that is what the instruction which will actually put the data into the LED set you have. Right? Okay, what is next? Tell me. Move AL, comma, 10H. Okay, out 9CH, comma, AL. Next, move AL, comma, 08H. Out 9CH, AL. Next, move AL, comma, out 9CH, comma, AL. Next, move AL, comma, out 9CH, comma, AL. Next, move AL, comma, 01H. Out 9CH, comma, AL. Done. Now, how do you repeat it for n number of times? Just put a counter. See, move CX, comma, FFH, move CX, comma, FFH. Now just give here what? Loop up. You come here. Loop up. Done. This will continuously give an effect of running light, running light. This is the way you write a program. But here we have not used 855 now. We have used simple buffer. Okay? Have you understood this?
CX9 is inside the
Which one?
move CX, comma, FF.
CX, comma, this is the loop. Okay, I'm putting a counter in the CX register. Okay?
No, it is inside the statement or outside?
Which inside? It's outside, outside, outside. See, this whole thing has to be repeated, right? Programming, my dear. Have you understood this? Okay? So, this is what actually an interface. So, I have already explained you about this. Now, suppose if I say my address is, say, 4CH. What changes I have to do here? What changes are going to happen here? 4 means it is 0, 1, 0, 0. C means 1, 1, 0, 0, right? So what changes I have to do here?
The ones which has been removed.
Come on, tell me. Where and all I have to put the NOT gate? Where and all I have to? I should get 0 here, right? That means I should get all 1, 1, 1, 1, 1 in here. So how do you get it? So here you put one NOT gate, right? Do you require this NOT gate? Here require, right? You have to put 1 here. So here it is not required, here it is not required. Now it's correct. It's correct. This is a small changes you have to do. How we got it? Right? I have changed this to 4CH. This is the circuit. Suppose if I make it to say FFH, tell me. My address is. So this is in. Okay. I'm just asking you the previous one. Here, suppose if this is FFH, can you tell me what is the changes you have to do?
All of them should have.
There is no NOT gate. There is no NOT gate for all these things. This is for now out. This is for out. Data out. Can you tell me? Suppose if you want to get the data input, so what is the requirement? Suppose if you are getting the data from the input device, see, data is coming inside now. Same thing, same circuit applies. Right, same circuit applies. See, only instruction is different. You have instruction in AL, 9CH. Right, same, address is same. Okay, of course, when it is 4C, it will change, FF, it will change. Right, your circuit will be similar. Instead of write signal, you will have read signal, because now data is coming inside from an IO device to the 8086 microprocessor, from outside to 8086 microprocessor. Right? This is the way you interact. Your microprocessor, your 8086 microprocessor interacts with the IO device. Just out and in instruction. Now tell me, I told you there are two types of interfacing, right? IO mapped IO and memory mapped IO. Okay? IO mapped IO and memory mapped IO. This is an example for which type? IO mapped IO. Please remember that, okay? It's very important, okay? So, as I told you, interfacing input devices like switches required buffers. Interfacing output devices required latches, okay? The programmable peripheral interface PPI provides these features in one chip. Okay? The 8255 is a separate integrated circuit which will provide lots of facilities which is programmable to connect various IO devices to 8086 microprocessor. Have you understood this now? Okay? Fine. So maybe next class we will try to use 8255. Okay? 8255 is very important. That maybe the last few topics in this microprocessor, and it's very important also for you, right?